correct. And as I could already see, there was the first question. Who picked the logo first? Was it Novatec or was it Meta? It was, of course, Novatec. And we're in a big lawsuit with Facebook now. No, it's not exactly the same, and but we didn't want to change it afterwards. But we really get this question very often. So, welcome to my talk. Thanks for joining. Hope you all had a great lunch. This is actually my second talk today. So quick question, who has been at my first talk this morning? Okay, so thanks for coming back. Also, a quick disclaimer, there will be a bit of an overlap, especially when it comes to introducing service mesh and Ebpf. Apart from that, it has a totally different focus than that. So just like as a note there. Now, quick introduction about myself. Yeah, I work for Novatec, not for Meta. That's probably where people might eventually know me from. What people don't know normally is that I'm also a university lecturer, so I do that twice a year, for the subject of distributed systems. And this is also kind of where this talk originated, because distributed system is a bit of an old and dry topic. So what I try to do then is to do distributed systems kind of with modern technologies. And so these are options with technologies that I would consider as kind of modern to implement distributed systems behavior and fulfill distributed systems requirements. Now, before we're gonna go into that, we first gonna basically do a bit of a why would people actually do distributed systems and how, and then look into the various options of how you can do that. So standalone frameworks, Kubernetes, service meshes, Ebpf, and maybe find a conclusion there. Most likely I won't be able to give any live demo on that talk. I did the initial version for this talk for the Spring I/O conference, and I had 50 minutes there, so it's a little less today, so this probably won't be able then. Now, the question in distributed systems, I mean, people that using containers and working with Kubernetes probably are very familiar with that, but of course, sometimes you need to ask yourself, why would you actually distribute a system in the first place? To basically say, why one is split one problem into many problems. In the end, to the consumers of your application, it still should appear as one system, no matter how much you split it up internally. Oh, I got a presenter, I can use that. So, one reason, of course, could be that you say you want to run different tasks. Tasks in parallel, tasks independently, and altogether, we should fulfill one goal. Another option or reason might be that you're running on different operating systems and you cannot run them all on the same system. Or going more in that direction, which is probably often the case in a Kubernetes environment, you're using different languages and different frameworks. Basically having a polyglot environment. Or even if you stick to one language, or framework, like here Java and Spring Boot, you still might have version differences, and then still you cannot run the entire stack in like one process. All right, more than that, of course, distributed systems allow you to easily extend the system as it's kind of distributed already, so it can easily grow over time. So that's like the first half of reasons why you would do that. And they're more like on the heterogeneous kind of side of things. The other one are more like on the scaling and redundancy side of things. So of course, you might want to do distributed systems to say, I want to increase the availability. So I have 4 systems of the same type, and one goes down. It should still be fine for my clients because the 3 other ones are still running. In an ideal case, they shouldn't even know it. With that redundancy also, you can do load balancing. So if your users increase and your requests increase, you might want to distribute the load to make sure everything is covered. Or in another form, you might also want to block it. So either you have too many requests and your systems might be threatened to go down, or you might have some kind of denial of service attack or whatsoever, then it would be good to have a system that would block the traffic in order to keep the systems healthy. Like a modified form of that is like rate limiting, to say, well, I don't want to get all the requests, but I want to leave enough requests through so that I can partially satisfy my clients and still have the running systems. And in the background, I might just like scale up to new ones. Security, of course, is an option, or like a reason to say, well, not every request should be allowed to get through. And also, in the context of downtime or availability, you might want to say, if I roll out a new system or a new version of my system, I don't want the system to stop. So I want to get the new one out while the other one is running and switch the traffic to the new one. A more advanced form of that is basically percentage routing or canary deployment, where you say, I don't want to like switch in one go. I might balance the traffic and roll out the new one either over by reasons of percentage or by the origin of the request, to basically do it only for specific countries or whatsoever. Like as we've been talking of Meta, Facebook does that very often to deploy new features only to special regions, and then if it works fine, they roll it out all to others. So this is at least my idea of why people would use distributed systems or where it makes sense to use them. So if you want to build them, you need a couple of things to get implemented. Of course, this is pretty obvious. The systems need to communicate. Otherwise, it doesn't make a whole lot of sense. So they need to speak the same protocol to do that. And you need that kind of networking component in various spaces, where you say, this one reacts on the incoming traffic, and either it routes the traffic to various destinations, it distributes it, or it throttles or blocks it. With this one, you can then achieve a lot of those functions or like implementations that I showed in the reasonings before. Something else is like what you most likely will need is some kind of a telephone book, like a service registry, so that the services will actually be able to find each other. So when a service starts, it needs to say, well, hello, I'm there, and I'm service X, and then if somebody else tries to query service X, it can look it up and talk to it then. That will help to make it easily extensible. Another requirement is also to roll out configuration to the various components. So if you want to have a specific update and there's configuration which affects several of your components, you don't want to go around one by one. You might want to have a source that can update things dynamically in one step. And on the side of error analysis, of course, you would like to have distributed logging, tracing, or observability. Observability I have covered already this morning, to figure out, are they all doing fine? And if they're not, how to figure out what can go wrong. So I've created this kind of sample diagram of a distributed system and on a small scale, where we see we have like 4 different services. We have like a kind of a proxy inbound, like an API gateway. And then you see if you have a service registry and the configuration and observability, each one of the systems, of course, needs to be connected to that. So even though it's pretty small, you can already see the problem with the complexity there. And then, of course, you can start trying to do those things, like service A, deploy a new version while the old one is still running, and then use the proxy to switch the traffic, or scale service D so that C basically can load balance across them, and hence improve your let's say, reliability of your overall architecture. Now, in the time before containers and Kubernetes, this problem already existed. There were companies that had large-scale software deployments, and they needed a good response time and availability, and one of those companies was Netflix. So Netflix created the Netflix open source software, where they built functionality for exactly those problems, like Eureka as a service registry, and then Hystrix as a circuit breaker, Ribbon for load balancing. So I'm not going to read through all of those. So, but that's just my sample or reference for how things would be done in a software framework as opposed to in a platform. So this one kind of, and if you imagine or go back to this routing traffic shaping thing, then you would see you could use that for various functionalities, like either routing to different destinations, distribute it for load balancing, or block and throttle it in terms of circuit breaking. Now, this one didn't continue forever. This was kind of taken over by the Spring Cloud implementation. So Spring Cloud took over those implementations, and this one is still being used and maintained today. The way that works in such a framework setting, of course, you need to do your things individually on the various components. Like, for example, looking into the service registry. I mean, this is a Java example. Of course, as it's Spring Boot, you would have to add dependencies, and you need changes in code. So that's a big difference, as we see later on, if you do it with a platform, because you have to change your code and rebuild the application. Now, but if you do it that way, you're basically independent of where your applications run. So they could all run as individual processes on one machine, or they could run on different hosts. They could run in containers, or wherever. So, but from the perspective of the application, it doesn't matter then. So it doesn't really need to rely on where it is running in order to fulfill this functionality. Now, this is the part for the framework. So we can see this happens on application level. Again, you need to combine dependencies, code and configuration properties, but it makes it underlying. It makes it independent of the framework or the underlying runtime, and it's pretty lightweight because you can place the things dedicated where you need them, and you don't place something which would solve all the things, and you might add additional overhead that you don't actually need. So Kubernetes, of course, changed things here a little bit. Now, when Kubernetes arrived, and you probably know that, things are running in the containers, and these containers are being run in pods. And Kubernetes brought along many own functionality that would go into the same direction. So Kubernetes has an own service registry, like etcd and the combination of etcd and core DNS. Then for external configuration, there are config maps. Observability, as we've seen in my other talk, there are too many options, so I'm not going to talk about that much. But with things like a deployment, you can do those updates. Kubernetes service, which we'll see in a second, will enable the communication and register these things. So Kubernetes had this, of course, this thing totally in mind to facilitate distributed systems behavior for independent of the application. So, for example, one good example here is the Kubernetes service. In that case, it's a cluster IP. So once you expose things as a service, it fulfills a couple of things. First of all, it enables the communication, but then it also registers itself in the service registry. And with that selector, it also enables the load balancing. So if my replicas scale up on a deployment, this selector will basically load balance across all instances that it can find from that label. So this is, of course, pretty helpful there. Now, config maps and secrets will fulfill the possibility for external configuration. And so you can inject the same configuration into multiple objects at the same time. It's not so easy to update it so dynamically, so you still might want to use something with like a config server where the configuration can be pulled, but nevertheless, there is an option to do so. So, yeah, this is the Kubernetes part, to say a lot of the things come here out of the box. You don't need to do anything yourself to facilitate that behavior of the distributed systems, like scaling, load balancing. It's all there. However, what Kubernetes does not provide out of the box are those resilience patterns. So you can configure the routing. It's not the objects are not traffic aware. There's nothing like retries or circuit breaking. These are the things that you potentially have to add if you need them. So one of the things how you can do that is service meshes. So these are slides that people might have seen this morning already. In the concept of a service mesh, you add a proxy container into the pod of your application. And this, if you have multiple containers in a pod, they share the same network. So they see all the same traffic. But not just that. It's not only useful for visualizing or for listening on the traffic, it also can be used for interacting with that traffic. That means, for example, it can block the traffic, or it can encrypt the traffic, or it can route the traffic somewhere else. So if you do that for all your applications in your distributed system, then you can influence the behavior of that quite a bit. So another important aspect is it's completely independent of the language or the framework the applications are written in. So of course it will work if everything is Spring Boot, but it will also work if none of that is Spring Boot and everyone has a different implementation. So that makes it, in this case, a lot stronger than if you use a framework. The other good thing is you don't need to rebuild or restart your application. You can basically just add it to the running pods and then control it like that. So then you will have the possibility to interact with your network traffic better. So, first of all, you would add this kind of routing component into each and every pod, and then you start getting control over it. So now you have this control plane, which will reach out to all the little agents, and then you can not only observe, but also interact with it. And already seen from that picture, you can see why it is called service mesh sometimes, because of course it adds an additional level of network complexity. But then you can do things like say, okay, I want to go sure that the traffic between those two components is secured, or I want to make sure only this traffic is allowed. So you can say, create a virtual service. This is like a CRD that comes along with a service mesh, and say, well, okay, if somebody goes to that destination, it's only allowed if it has that source label. Other traffic will not be allowed. Another thing is also the traffic distribution, where you can say, okay, I want to do this kind of canary deployment, and say, well, this destination A, has a so-called weight of 75%, the other one only about 25%. And then it's also easy to tweak and turn that. So if you realize your new application doesn't work so well, you can easily switch it back. So these are the sum of things that you can do there. It's not only security and the traffic switching, but you have all those things like retries, circuit breaker, and so on. In the end, this is pretty similar what API gateways or ingress controllers do, but normally you have those only at the entry level of your application. If you find yourselves, you deploy multiple of them, like in your application, it might be better, of course, to use such a service mesh because the configuration is much easier then. All right, and with that, you can then do things like, in this example here, so you see I'm rolling out a new version. It is currently, the old version is at like 100% right now, and then I can switch that, and then the traffic starts to distribute, and the new one starts to pick up. And that normally works quite well. All right, this is also what I already said this morning a little bit. So this, of course, comes with a price, because as you can see here, okay. And here, you have this little proxy component in each and every of your pods. I also had some questions this morning in the other talk where people didn't seem to be so enthusiastic about that because people are probably fighting with the latency and the overhead that the service meshes generate. If this is something for you, you need to decide. But given here, you can basically see, do I really need to do those things? I mean, do I need percentage routing? Do I need dedicated encryption between the services and so on? There definitely can be use cases, but I would not recommend to say I'm going to set up my Kubernetes and will use a service mesh straight from scratch, and everybody needs to work with it. All right, so yeah, it basically extends your Kubernetes for the limitations that I said before. So it is traffic aware, and then you can shape the traffic and work with that. This happens by injecting sidecar proxy into the pods, and then you get control over the entire flow. All right, so Ebpf has already been mentioned in a couple of presentations today and yesterday. This is a pretty emerging technology at the moment that tries to improve that problem that the pod-based service meshes have, so that you don't have to inject all the pods with an own agent and to put that agent somewhere else. The way that it works, I'm going to cut this a little short because I think I'm running out of time, is that you put the Ebpf in, it's a Linux kind of kernel technology, and it runs and you have the possibility to inject custom code into a sandbox in the kernel without the possibility to really harm the kernel. At least that's what I think. In this way, this sandbox code can interact with the network flow, because network events are also kernel events, and then react on those and change the behavior or execute commands based on whatever it's being monitored. Now, each Kubernetes worker node is such a Linux node. That means it will work on the node level of your cluster architecture and not on the pod level. So if you can see here, we have 3 nodes. Then you would basically have 3 kind of edge components or proxies, which would feed all the information into a control plane to change something there. So if we look back at this picture, in this case, your pods and your running applications will totally be untouched, and the routing component will just sit right on the nodes on the bottom. And that way, it can also feed pretty similar information to a control plane, what traditional or pod-based service meshes do. And now you can, like, in a similar style, it comes along with own CREs, where you can change the way the network interacts. So this is like an example for a Cilium network policy, which works fairly similar to say, okay, it checks on labels and then can decide, okay, is this traffic with an incoming label allowed to go there or route it somewhere else or whatsoever. All right, so right now there is a service mesh from Cilium, and they are just adding features over time. I don't know exactly, because I haven't played with the last version yet, what they currently have implemented. They have implemented observability already and some traffic shaping things. They did this survey a while ago to ask people what they would be interested in, and most likely all of those things are going to come over time. And then it's going to be really interesting to see if this is something which could replace the way we've used service meshes in the past, in case we have used them. This is just a screenshot from the observability part of the things. And just to see, it's actually pretty straightforward. You place it on the nodes, and whenever you deploy new applications, they don't need to get pod injected like in a traditional service mesh, so they just would run like they run without any service mesh implementation. All right, so to recap that, instead of pod injection, you have here like a node injection, and you leverage the Linux functionality for Kubernetes that is initially coming from the BPF and is now called like extended the BPF for your distributed systems network behavior. When I put up a similar slide this morning and said early stage of the development, Liz Rice came to me and said, well, it's still early in development, but it's already used quite a bit in production. So I promised her to correct that. I didn't correct it on the slide yet, so I'm going to tell you. This is already production ready, and I'm pretty sure we're going to see a lot in that space in the future. Now, to wrap things up, which is, it's of course difficult to say which one is better. So running things as a process, running things in Kubernetes standalone, using sidecars, using eBPF, and so on. I mean, the question most likely will be in the first place, what do you really need? And how much do you want to be bound to your infrastructure? I mean, I'm a big fan of Kubernetes, but I also would say Kubernetes is not always the solution for every problem. So sometimes it might just totally be okay to implement those kind of behaviors of a distributed systems with frameworks that programming languages give. And then things can, of course, still be run in a container or added to Kubernetes at a later point in time in case you really think you need it. And same goes for service meshes and Ebpf. Of course, it's a lot of fun playing with those technologies and seeing all those things, but you always need to be aware what kind of price that you want to pay for that. And I've probably seen more cases where people tend to over-architect their infrastructure and provide more feature than actually needed than the other way around. So this is basically what you, of course, need to decide. And the good things with those technologies, and that's what I also try to show, is you can easily add them over time, and if they don't fulfill what they basically promise, it's also easy to take them out again. All right, I think that was it. Maybe I was talking a bit too fast now, because I thought I would not make it in time, so sorry for that. But yeah, first of all, thanks for listening. And yeah, I should probably add, I forgot to say that, we don't not only have speakers here, we're also sponsoring this conference. We have a booth, and we're going to give away a Nintendo Switch, I think, this afternoon. So it's still time to go there and sign. Do you want to have? Well, you can try. Get a fair chance like everyone else. And yeah, if you have any more questions, you can, of course, ask them now. If we don't have enough time for that, then you can still come to the booth and see me there. All right. Do we have questions?
Okay, thank you very much. Aside of the one I think you already saw, which is
this was the opening question.
Any questions in the audience?
Thanks for the compliment. I mean, of course, if you, I don't want to just ask questions. If you think there is something which I should include in future presentations, something that should be mentioned for implementing distributed systems behavior, please let me know. I mean, obviously, I have a bit of a Java background. That's why I know the Java frameworks better than other ones. You don't need to do Spring Boot or Spring Cloud to do that. If you, for example, Quarkus and Micronaut are alternative technologies for distributed systems with Java, and they have an own set of features to achieve the same things. Maybe worthwhile to note is that they have come up or became popular after the rise of Kubernetes, so they already have a better integration with the Kubernetes or rely more on the technology of Kubernetes with the implementation as opposed to Spring Cloud. Does Selenium Mesh already extend across clusters? Well, according to what I've read, yes. I mean, I don't work for Cilium, so I don't know it exactly. I haven't done it myself, but I've heard that you can use Cilium also for cross-cluster communication and enable the communication from pods in one cluster to another one as if they were running in the same pod. But if you really want to know it for sure, there is also an ESO Valent booth. They're probably more than happy to explain that. And I think for the second one, I also need to guess. I don't know it exactly, but in my opinion, they can be used for namespace isolation in a similar way as Istio. I mean, also the control plane runs in a dedicated namespace similar to Istio, and it has access to the components running in all other namespaces, and hence you can most likely isolate them by using label matching. For next time, demo please. Yeah, I mean, I think I can try to set something up and do that on direct request at the booth later on. So just come by. And yeah, I mean, I can, when I did this there's a YouTube recording from this presentation from the talk in Barcelona. This has a bit of a demo, so you can try to find that. Well, I think Istio will consume more cluster resources. By the nature of things, I mean, both are using an Envoy component as a proxy. And the memory consumption or the resource consumption is, of course, how often you instantiate it. More than likely, you will have more pods than nodes. And in that case, the resource consumption with a pod-based service mesh is higher than with a node-based one. The worker nodes will, of course, be affected in a way that they need to run that component. And I think there are some other changes that are being done. If I'm not entirely mistaken, it exchanges the kube proxy with an own proxy to intercept the traffic there. But again, my knowledge is probably not deep enough to go there. I mean, the reason why I brought it up today, I just see that also in our implementations, this is an emerging technology, and it's probably worthwhile to get into that. Good enough?
I have one question.
Yeah, sure.
So we hear about Istio, Cilium, Linkerd,
yes,
console. What would be your advice for someone that just discovered what service mesh is? Which one would you recommend to use first, and then probably move to a deeper integration?
I mean, I don't know which one I would pick first. I mean, the good thing with all of those technologies, they're super easy to try. I mean, you can easily spin up either using like kind or like small-scale Kubernetes cluster on your own machine and start implementing and try them out. It's not a big deal to install them. And for both Istio, or Linkerd as well, of course, and Cilium, they're pretty helpful explanations given on their website. So to set it up and play around with it, and then compare by yourself, probably won't take a lot of time. So I don't want to make a real preference here. It's again, Istio might probably be a bit more mature as it's been around longer, but it will in turn definitely have more consumption. So yeah.
Okay.
I don't want to make a pick.
One last question.
Has anyone done any benchmark of size?
Good question. Well,
I don't have. I haven't made such a benchmark, so I don't know. I think this might also be something to address at the Cilium people, because of course their pitch is definitely to say they have lower latency and lower consumption, and how this. But of course you would get probably a bit of a biased opinion there. To be honest, I don't know. I don't know if there is.
Okay, thank you very much for your talk. Thank you for answering all those questions. A big round of applause, please.
Thank you.